Hello everyone, this is Algebra 2, 10.3, Composition and Inverses of Functions. Today we're going to talk about what happens when you have two functions that are working together to accomplish a goal. So sometimes we have one function that does one operation, another function that does another operation, and we want to put them together to put their operations together. And that's called composing or composition of functions. So when we put the functions together, it's going to look something like this: f of g of x, or it might be g of f of x. So we've got a function called f of x, a different function called g of x, and here the g function is inside the f function. Over here, the f function is inside the g function. We're going to talk about what that means. So from your book, on page 463, it gives you the definition of a composite function. So I went ahead and wrote that out here. The function whose value at x is f of g of x is called the composite of the functions of f and g. The operation that combines f and g to produce their composite is called composition. So what we're doing is we've got g of x is giving us some directions, f of x is giving us a different set of directions. We're going to follow the directions for g of x and get an answer. Then we're going to take that answer, plug it into f of x, and get a new answer. So we're going to look at what that means for evaluating it at specific values, and then we're going to talk about what it means in relation to the graph and other things like that. So for our first example, we've got two functions. If f of x is the function the square root of 2x, and g of x equals x plus 5, we're going to find the following. We're going to do a few different things with these two functions. So first of all, we're going to find f of g of 3. So the way we work with composite functions is we move from the inside out. Kind of like when you're working with the set of parentheses. You start with the most innermost set and then you work your way out. So first we have 3. 3 is being plugged into the g function. So we can do that first. We can first do g of 3. So that would look like 3 in place of the x in the g function would be 3 plus 5. So g of 3 would give us 8. Then if we go back over here to our composite function, once we know g of 3, we're going to plug that into f. So next we're going to do f of 8, because we're going to take the answer that we got here and plug it into the f function, which is the square root of 2x. So we're going to have the square root of 2 times 8, which is the square root of 16, and that gives us 4. So f of g of 3 equals 4. We first put the 3 inside the g function and solved it, and then we put that answer inside the f function and solved it. We worked our way from the inside out. So let's see what happens if we go the other way. What if we do g of f of 3? So I'm still using 3, but this time I'm going to put it in the f function first, then I'm going to put it in the g function. And I want you to be thinking about, just guess, do you think this is going to have the same answer as before, or do you think it might have a different answer? Let's see what happens. So first we're going to do f of 3. So if we go to the f function, it's the square root of 2x. So we're going to have the square root of 2 times 3, which is just the square root of 6. That doesn't simplify, so we're going to leave that. Now we're going to take that and plug it into the g function. So we're going to have g of root 6. If we go up to the g function, remember it was x plus 5, so this is going to be root 6 plus 5. These are not like terms, so I can't combine them any further, and there's nothing that simplifies, so that's the answer. So this is different than what we got the first time around. So when we plug 3 into g and then into f, we get 4. When we plug 3 into f and then into g, we get root 6 plus 5. So you don't necessarily get the same answer, even though you plugged 3 in both times. You got a different answer based on the order that you did the operations. All right, the other thing that we can do with this is we can compose the two functions and write a new function. So if we have f of g of x, so this time I'm not going to be plugging any numbers in. I'm going to put g of x everywhere you see an x in the f function. So I'm going to replace x with g of x. So in the function of f, which is normally the square root of 2x, I'm going to do the square root of 2, but in the place of the x, I'm going to replace it with g of x, which is x plus 5. So I put the g function inside the f function. And then if you can simplify that, you want to simplify. So here we're going to multiply with our distributive property. This is going to give us 2x plus 10. And that does not simplify any further. So this would be the function f of g of x. Now we could go the other way. We could put f inside of g. So if we do that, g of f of x, we're going to put the f of x function everywhere we see an x in the g function. So we're going to replace x with f of x. So instead of just having x plus 5, we're going to have root 2x plus 5. So wherever there was an x in the g function, I replaced it with the whole thing f of x. So this is g of f of x. This is the f function inside the g function. Notice it's different than f of g of x. So whichever one goes inside the other affects the answer. It gives you a different outcome. Now we have another function that I want to talk about that's going to help us explain this next piece. There's a function that's called the identity function, and we use a capital I for this notation. So the function capital I of x equals x. This is called the identity function. And this function works a lot like the multiplicative identity. So remember that a times 1 equals a. If you multiply something times 1, it keeps its identity. The identity function, if you have f of I of x, it equals f of x. So if you plug the identity function into a function, the function stays the same. Just like if you multiply something by 1, it keeps its value. If you plug the identity function into another function, that function keeps its value. This comes in handy when we're testing two functions to see whether or not they're inverses of each other. So two functions whose composite is the identity I are called inverse functions. So this is a special kind of relationship between two functions, inverse functions. Two functions whose composite is the identity I. Now, I'm going to show you what that actually looks like for practical purposes for what we're going to do. So when we're working with inverse functions, this is what we're actually looking for. So for inverse functions, the functions f and g, we use those two the most, but you can use h or I or j. So the functions f and g are inverse functions if two things, f of g of x equals x and g of f of x equals x. And this is for all x's in the domain of g, and this is for all x's in the domain of f. So if there's something excluded from the domain of g of x, it's also going to be excluded from the composition of the functions. So what is this saying? Sometimes we read these rules and we're like, okay, that's great. What does that even mean? Let's look at what this is saying. When we put the g function inside the f function and we simplify it, and it simplifies out to x, then we take those same two functions and we reverse it. We put the f function inside the g function and simplify it out, and it also comes out to x. If both of these things are true, then these two functions are said to be inverses of one another. And inverse functions can do some cool stuff. We're going to talk in the next lesson about a specific type of inverse relationship between exponential functions and logarithmic functions. So that's something for you to look forward to. But for right now, we're going to look at how do you show that two functions are inverses of each other. Knowing this rule, how do we show that two functions are inverses of each other? So show that the functions are inverses. This is kind of like a proof. Not formal like in geometry, but you're proving something to be true. So show that the functions are inverses. So if we have the first function f of x equals 1/3 x minus 1, and our second function g of x equals 3x plus 3. What we're going to do is we're going to use this rule up here. I'm going to do f of g of x, and I'm going to see if it comes out to equal x. If it does not come out to equal x, I'm done. Because if one of these is not true, then they are not inverses. But if this one comes out to be x, then I need to keep going, and I need to try g of f of x. If that one also equals x, then I know that these are inverse functions. So if one of them is not, then they're not. But you can check the other one just to check your algebra and be sure. All right, so let's do f of g of x. So again, I'm putting the g function inside of the f function. So looking at the f function, where there's an x, I'm going to plug in 3x plus 3. I'm putting this whole function inside in place of that x. So I've got 1/3 times 3x plus 3, and then this still has a minus 1. So don't forget that little piece. Then I'm going to distribute the 1/3. So 1/3 times 3 gives me 1x. 1/3 times 3 gives me 1. So I have x plus 1 minus 1, that equals x. That's good. That's what we were hoping for. So once one of them is true, you have to also test the other one. You have to show both. So if we do g of f of x, now we're going to go the other way. Inside the g function where there's an x, I'm going to put this whole f function in that spot. So I have 3, and then in place of the x, I'm going to put this whole thing 1/3 x minus 1, and then don't forget this plus 3 at the end. All right, I'm going to distribute again. 3 times 1/3 gives me 1x. 3 times -1 gives me -3, and then I have plus 3. X minus 3 plus 3 equals x. Hooray! According to our rule, that's what we were looking for. So when they are both true, when f of g of x equals x and g of f of x equals x, then we have inverse functions. So now we can say that f of x and g of x are inverses of each other. When you're talking about inverses, you might come across a new notation that you haven't seen before. So the inverse of a function f, the inverse of a function f is usually denoted it looks like this. It looks like f to the negative 1. We are not actually raising the function to a negative 1 power. This is a notation. This is not a mathematical operation. So this notation, we would read f inverse. So if you see that little notation on a function, if it's talking about two functions and it says f blah 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 and then f to the negative 1 blah blah blah, what they're really saying is that you've got a function f and then you've got the inverse of the function f, and that's how they use the notation. Hopefully this will help you with composition of functions. If you have any questions, you can email me. My office hours are Monday through Thursday, 10 a.m. to 11 a.m., but I'm checking emails a little more often than that, so feel free to send a question anytime. I will answer it the next time I log into my email. So if it's not during office hours, you might not get an immediate response, but you can email anytime and I'll get back to you the next time I log in. Let me know if you have questions. Hope you're doing well.